All right, let's get started. Hi everyone, hope everyone is doing well. Today is lecture 2, and we are going to be talking about image classification. It's one of the core things or core tasks in computer vision. And we'll see how that acts as a building block for robot perception that we care about. Before going into the most interesting part, let me cover a little bit of logistics. So project 0 is out. I don't know how many people have checked it out. Raise your hands. Cool, awesome. So it uses Python, PyTorch, Tool Collab. So it's basically getting yourself familiar to the rest of the projects in the semester. It's due on Tuesday. So if you haven't started, I would highly encourage you to do that and finish it up. It does take a little bit of time because there's so many portions to it, but do it as early as possible. I will send out a link where you can submit your zip files. I'm working with the tech support to actually establish an autograder so that it can be more autonomous later on. If that is not the case, I'll provide a Google form. You can submit your zip files and I'll do the grading. Cool. Okay.
So with the auto grader, like, do we get immediate feedback when we do that so that you can look at where the mistakes?
Yes. So autograder provides we kind of set up like 2 attempts per day where you can submit and it throws out an error depending on what we're expecting. That will be easier for the rest of the projects because we want to evaluate everybody with the same lens, and it also provides you ways to submit and see what happens to the other test cases that we have. So yeah, we want to make that happen, but I'm still working with the tech support here, so we'll see how that goes. But for the first project, I think it should be fairly easier compared to other projects. So you can submit the zip file, that should be fine. But yeah, I'll send out a link and an announcement. You should be hearing that tomorrow or maybe on Saturday. Okay. So project 0. So at Michigan, they had this issue. I think we fixed it. I think if you open your Jupyter notebook, it should be 1.13. This is actually a problem if you are trying to develop locally. I think by default, the version that we gave earlier was 1.10, but I think we fixed it. But if you have this issue, try to fix it. If you have CUDA issues, try to fix the PyTorch version, and that should resolve the problem for you. Okay. Make sure you save the notebook file before you submit, because then we have the outputs of your scripts already in the notebook file, which is what we will use for evaluation. And close any collab notebooks. Like for instance, don't leave it on before you go to sleep or something. Try to close it as soon as you finish your work. And especially try to make sure you do this close to the deadline, because Google can say, okay, you passed the limit for the day or something like that. We don't want that. So try to close this as soon as you are done with the work. Okay. So discussion forum. I know some of you have filled in the Google form and accepted to opt in. It's a great place for discussing with other students. Even if you have any smaller questions, you can see what people have posted earlier. So I wanted to give a snapshot of what it looks like. So it's basically like a piazza. So this is a snapshot. There's a bunch of discussion already happening because as I told you, Michigan is 2 weeks ahead of us. So they are already done with the project 0. They're working on project 1, I believe. So yeah, so it's a great forum, but again, it's optional. You should use the Google form, which is on the syllabus webpage, of the course website. So look it up. Okay. Enrollment, I think additional permissions have been already given. If not, please talk to me after the class. I think the class is already full. The limit was 20. I think now the enrollment is 30, which is great. but we want to limit, still want to limit the numbers. Okay. Okay, so coming back to the interesting part of the lecture, image classification. So this is a core module or a task in computer vision community. People have been working on this aspect for a very, very, very long time. And we want to be able to use that for robot perception because we want to identify things in the environment and be able to act on them. A simple image classification example would be what you see in the slide. So there is an input image, and what we expect out of an algorithm or a module or a neural network is to output a particular label out of a list of labels that we have provided. It's basically choosing the right answer given an input image. So in this case, it's the chocolate pretzels. And the important thing to note here is that there is a semantic gap between what we see versus what is given to a computer program, right? For instance, we are able to immediately say that it's a pretzels or it's a bag of food, right? But this is what the algorithm or the computer program is actually seeing. It's seeing a bunch of numbers. And in this specific case, it's an RGB image, which is red, blue, green image. So it's a matrix of numbers, particularly here, 800 cross 300, 800 cross 600, and there are 3 channels, each talking about different colors. The other thing to note here is that as soon as there is a viewpoint change, for instance, if the camera is moved to a different location and we see a different set of numbers that we are inputting to the algorithm, right? It changes drastically. Even with a small change in the viewpoint, the particular portion in your image changes quite a lot. Now, that is kind of a huge problem when we are thinking about robot perception, because robot moves a lot. And we saw a glimpse of how the sensor data looks like in the last lecture. So it's a very difficult and challenging problem to be able to understand the scene, just like looking at the pixels. And there are other challenges in this image classification. So for instance, intra-class variation. So all of these are food items, like bag of chips or bag of pretzels, but you can see that there are variations to it. That even in this pretzels scenario, you have 3 different kinds. So there are variations that the algorithm has to deal with to be able to recognize what is in the scene or what is in the image. Now we also have want to think about what do we mean by categories and what do we mean by instances, right? Of different food items that can fall into that particular category. So it is up to the application or the domain to kind of decide what do you mean by a particular instant and what do you mean by a category. So you can say, I'm going to classify a bird versus mammal, right? But you can also say, I'm going to go in deeper into the mammal category and classify cat versus dog. So there are different variations and hierarchies in which you can think about the categories. So again, you can think about like in a small food court, there are humongous number of like these products, and the robot should be able to figure out what is the category, what is the label of a particular item. If you're asking it to fetch something for you, it should be able to do that. Now, we only spoke about one object isolated in the previous slides, but that is not the case for an agent working in an environment. So it would be looking at a scene, which means there would be multiple things in the scene which could confuse the system in being able to say, okay, what is or where is the pretzel in this particular scene? Or is this image actually a pretzel or not? Right? It's really hard because there's so much distraction from the background. And in addition to that, the other challenge that we have is the image resolution. So I think I kind of alluded to this in the last lecture, where I said like most of the image data that you see on the internet are well curated, well taken, but it's taken on like using high resolution cameras. Like, so on the left side, you see an iPhone 14 camera picture, Whereas on the right side, you see a typically used RGBD camera that is mounted on a robot, which is, in this case, ASUS sensor. So it's like 640 versus you're thinking about 4000 cross 3000. So the image quality depends on the hardware, but that can also affect the algorithm or the program that is doing image classification. The other thing that kind of bothers many of the researchers in the space is the amount of challenge that you get in the presence of illumination. So we want the robots to be in our environment, to be able to work with our objects the same way that we do. But we can handle different lighting situations, and we can say we can work with a specific set of objects seamlessly. Whereas for robot, even a small change in illumination changes the numbers that you see in the matrix, and that causes a lot of challenge in doing image classification. And this is actually a huge problem when it comes to robot perception, because even if you are working with the same set of objects, you have to handle different scenarios, different illumination conditions. And the object can be in different states. So in this particular slide, you're seeing object that is a deformable object. But imagine looking at a door, right? A door can be open, partially open, completely open. There are different states it can take, including your cabinet drawers, fridge, anything. They can have different articulation, different deformation, including a water bottle. It could be open or closed, but it's still a water bottle. So we should be able to accommodate all of these changes and still be able to classify that image with a particular label, and it's a huge problem. And along with the clutter that we saw earlier, clutter can also induce occlusions. So background clutter is that you have so much disturbance in the background, but what if those objects are in front of the target object? So which leads to partial observations, meaning you cannot observe observe all the pixels that constitute to that particular object. That is a challenge for image classification algorithms. So if you see clutter, and the clutter could also happen because, or the occlusion can also happen because of the robot actuator. It could be other objects that have some sort of transparencies, which kind of gives you a different data than what you expect out of the appearance of the object. So these are some of the challenges in the specific case of occlusions. And the semantic relationships are also very important, because when you come from using an image classification on a computer vision task to a robotic task, the robots at the end of the day have to act on these objects. So for instance, on the left side, you're seeing a pretzel bag next to a mirror and giving you a reflection. If you use a typical image classification or a detection algorithm, it probably gives you two different bounding boxes saying that there are two objects in this scenario. But when we look at it, when we take a closer look at it, we can say that the alphabets are kind of reversed on the other bag, and we can say it's a reflection. So now imagine if the robot actually tries to act on the other object, it could actually like break itself or damage itself. So these are some of the realistic problems that we have when we want to have robot to use these image classification algorithms and use the other motion planning or action algorithms to act on these objects. On the right side, there is another scenario where it's kind of hooked into a hanger, and we need to know that it is that is the case, so that the robot can actually go and remove it from that hanger. So these are some of the things that we should consider when developing robot perception algorithms. Now, outside of the domain of robot perception, image classification has been of great help in different domains. For instance, on the top left, you are seeing medical imaging. People have been using it to diagnose tumor. So out of the scans from X-ray, CT scans and stuff, you can actually try to find a malignant a scan by just saying that, okay, this particular scan belongs to a set of patterns that it has seen before to be having a cancer or something like that. On the right top, you see galaxy classification. Now imagine a probe that is going into the space. Now it can have multiple sensors looking at different locations or viewpoints. It could figure out where it is by looking at the other galaxies around the space. It can localize itself and kind of figure out where it is in the space, which we call like odometry problem. On the bottom left, you see trail detection. This is actually using a drone. So the drone is trying to figure out or follow a trail in a forest. So by classifying a frame to be, this is the straight direction or this is not a trail, it is able to navigate in that forest environment. On the right bottom, there is an example of how it is being used in agriculture to classify tomatoes from either it's ripe or not. So out of robotics, or in general, image classification plays a huge role in solving some of these challenging problems. And I think that is one of the big reasons for us to actually learn or start off with image classification when we're looking at deep learning for computer vision or robot perception. Okay, so let us see how one can think about image classification to be a building block for doing robot perception. So I'll give you a few examples to say how you can connect various blocks here. Now we talked about image classification, but the robot has to act on different parts of the environment, right? For instance, now if you're looking at this image, there are different portions of the same image that can have different labels. So earlier, given an input image, there was one particular label. Now we are talking about given an input image, a bunch of labels, and also the bounding boxes of these interesting regions. So this is what we call object detection. And the way people have started doing this was, instead of looking at the entire image, how about like crop a particular portion of image and then run that through our image classifier. So the image classifier can work with, let's say, any size of images. So as long as you provide a crop, it should be able to give a label. So let's say we start off with some interesting region on top, and the classifier says, okay, that's a signboard. And if you move to a different location in the scene or in the image, it should say, okay, that's a bunch of snacks. So this is assuming that there is an existing image classifier that can actually classify each of these portions of images that we are giving. And now if you move further, it can say that there is a robot, and move further down, it can say that's a piece of that portion is a floor. So this is how you move from image classification into object detection. So we were asking a question of what is in the image earlier, and now we are asking where is it in the image. Now there is the next block here is to figure out, okay, now let's say we figured out where the pretzel food bag is, and we want the robot to be able to grasp it. In order to get to that location, we need additional perceptual tasks, which we call pose estimation. So where we say, okay, now we figured out where the pretzel bag is, but the robot also has to figure out what is the orientation of this particular object, so it can reach out with its arm and grasp. So these are the three different steps that we generally follow in robot perception. One is what is in the scene, where is in the scene, and how is it in the scene, so that we can aid the robot to grasp and manipulate that particular object. So we talked about image classification leading to object detection, and then now object pose estimation. Okay, so now let us think about like how one would start off like implementing an image classifier. I know many people have probably have done this in a different setup, but I just want to give a overview of how do you do image classification leading to nearest neighbors and then k-nearest neighbors. So okay, so let's think about how would somebody write a program. So it's basically a classification of an image, which takes an image and outputs a label. And it's really hard for you to hard code this for many objects, right? For instance, if you're looking at only detecting, or only classifying a pretzel bag, what you could do is you can use old school computer vision techniques, such as finding the edges or corners, and come up with your own heuristics that says, if I find these characteristics with edges and corners, I'm going to say that the image has a pretzel bag, right? And it probably works for this particular image. And now if you have the viewpoint variations or different illumination conditions or the other set of objects that look similar, you're gonna come into a problem where it's not gonna work. It's not gonna generalize to other objects or other scenarios. So a prominent way of doing image classification is using machine learning, which is fundamentally a data-driven approach, where you collect a bunch of images and corresponding labels, and then you build up your own image classifier or train your classifier, and then you evaluate that on a new set of images that you have in your disposal. So in terms of coding block, it's going to look like two different blocks, where you have train, which will take in two things. One is a set of images and corresponding labels. And the second block is to predict, do a prediction on a test set, where you will take the model that was output by your train function, along with the set images to predict the labels. So this is how you will think about an image classifier. What you're seeing on the right side is the training set or the project data set that you'll be using for the rest of the projects, like 1 to 4, which will be, we will do classification, followed by detection and post-estimation. I will talk about the data set in a bit. Okay, so coming back to image classification, one of the most starting point for anybody who is coming into computer vision is to use MNIST dataset. MNIST dataset basically has 10 classes, which are basically digits from 0 to 9. And these are images that are 28 cross 28, and they are grayscale images. And you have about 50K training images and 10K test images. So this is a data set that is prevalent in the community to do image classification. And as you can see, this is very limited in terms of domain, and the number of examples are also very small. So it kind of does not translate very well in the real world, but this is a very starting point for anybody who is thinking about image classification. A slightly different version here. For instance, what you saw in MNIST is 10 classes, 28 cross 28 sized images. Now, in 2009, there was this dataset released called CIFAR, which is the same size in terms of the number of images in the dataset, and same number of classes, but the images are different. They are RGB images, and instead of 28 cross 28, it's 32 cross 32. Now the problem is slightly different, and it is much more challenging, because you have images that are from real world, like from nature, and you have classes that are kind of curated by the authors. For instance, aeroplane, automobile. Then you have bird. Then you go into multiple instances of mammals like cat, deer, dog, and horse, and so forth. They kind of chose this set arbitrarily to build up this data set. But people have started working on this to figure out like how they can scale up from, let's say, MNIST to wild images. Then comes CIFAR 100. In terms of classes, it's much more bigger. So that's the only difference between the earlier set and this one. It has additional set of labels, like including aquatic mammals, trees, and etc. After this, in early 2009 came ImageNet, which is very prevalent in the literature of computer vision. Even now, I think people use this as a building block to train neural networks. And the scale of the number of images is huge compared to what you saw in CIFAR 100. You are thinking about 1.3 million training images. The thing to note here is, earlier you did not see a validation set, but here you have a validation set of 50K, and there is a test set which is of 100K. The reason is this was part of a challenge where the test set was not released publicly. It was kept secret, so people can submit their code, and a centralized system would would run their code to see how they are performing. And it was done using looking at, I think, the top 5 accuracy. There is a metric that says, what is the top 5 labels that actually correspond to a particular test image. And using that metric, they kind of rank these submissions. And here, the size of the image is not fixed. The size of the image could be arbitrary. But then the training algorithms would resize that into 255 cross 255, sorry, 256 cross 256, so that they can output the label of the image. Now, again, think about the number of training images. If you remember, in the train block, along with the images, we need the labels. So somebody manually labeled all of these images. So we have this data set. So around that time, this was a huge achievement. And this data set was recognized by the community as a huge thing back in the day. And there is also a different version of ImageNet. For instance, you have 22,000 categories, which is not oftenly used. But you will hear ImageNet in the literature, or whenever you go to a computer vision talk, this might come into picture. Okay, so it's not only about objects, right? You can have data set that talks about the environment as well. Now, here is another example where it has 365 classes of different scenes. So it basically classifies the image as a particular room or a scene, like it could be a cafeteria, kitchen, field road, anything like that. And there are like many such data sets that came in the computer vision, and you can look it up. You'll see like hundreds and thousands of data sets right now in the computer vision. But these are like prevalent ones that's been mostly used in the community. And yeah, so this is the data set you will use for the projects. We call props. Props expands to progress robot object perception samples dataset. This is from Michigan. From my previous lab, or the core instructors. So they had a paper called Progress Labeler, which is used to collect data. You collect data and you can automatically label them. Label meaning the bounding box of the images along with the poses and stuff. So it was a paper that can give all of the 3 questions that we are going to ask. So we'll use this data set for the course. And in terms of numbers, this is similar to the Cypher 10. It has 10 classes, and each image is 32 cross 32 RGB image. You have 50K training images and 10K test images. If you look at the objects, these objects are from indoor environments because we care about domestic robots helping people in the future. So we would like to see the scenarios where objects can interact with these objects. Robots can interact with these objects and doing meaningful tasks. Yes.
Would you happen to know exactly why these data sets typically have very low resolution images?
Because they have been collected using the robot.
Okay.
So to expand a little bit on how this has been collected is we had like tables, a bunch of tables and objects on them, and the robot would go around it. And that would give us like a video of RGBD, where D is the depth. And we would use this entire sequence in one episode and annotate all these objects. So we have the paper has an automatic way of like for a particular video, you can collect ground truth labels for all the frames in a single go. Yes.
I have a question. So, I mean, this is more looking at presentation. Were you guys specifically taking pictures to do the robot, or were you just grabbing frames from the video?
We were grabbing frames from the video that was taken by the robot.
It's not the way, in fact, you're stitching images into a video.
No. So it's basically going around. And the reason we use robot is we get the location of the camera at every frame. So we know with respect to the second view where the first view was. And we use that information to do the annotation later on. So we get a 3D world or 3D, multiple 3D scans, and there is an interface that we use to load all of this, and a human is annotating that. Yes.
You're saying, you're able to like automate the labeling of it. How does that work?
Oh, so in this project, in this course, we are going to use the data that was generated by the process. So it worked out really well. That's why we have a data set. And you can collect more data set with that. You can collect a data set for, let's say, transparent objects or objects of different categories. So right now we chose this 10 classes, but you can expand and look into multiple objects. Yes.
If we're collecting from a video, let's say the video camera takes 15 frames per second, but wouldn't the 15 frames be the same identical as well? So wouldn't that affect?
So the robot is moving, and let's say you get 15 frames per second. I think there is a way to not use all the frames. We might use, after a set of frames. I'm not entirely sure like what exactly that number is, but yeah, we can play with that number when we are annotating. Or it could be the scenario where it is moving, stopping, moving, stopping, moving, stopping. So you probably don't have any blur. There was one.
That's gonna be my question is, what the video was taken while it was moving, it wasn't stopped and shoot.
I mean, we can take it like anyways. I think maybe if I'm right, they would have stopped it for every and then take the image. Yeah. Cool. Good questions. Yes.
So if you wanted like the robot to detect images while moving, would you need training samples of moving pictures like with blur or not?
So you probably need a sophisticated algorithm that kind of de-blurs it. And the way people approach those problems is that the input to the neural network or the learning algorithm is not just one image. It's going to be a bunch of images at the same time. And it will be a recurrent, meaning it's going to keep looking at the next frames to be able to predict what's happening. So there's sort of a memory that is involved in those networks or in that particular application. Cool. Okay, so just to give a snapshot of like when you look at data set, I think we should also understand the aspect of like what is going into these data-driven algorithms. So the y-axis is actually in log. So there is a significant jump that you are not seeing here. Just for the sake of plotting, we are using this. So there is a significant jump from MNIST to CIFAR. And then from then on to ImageNet, there was a huge jump. And imagine like a function or neural network should understand the huge number of pixels. We are talking about pixels here to be able to classify images. And again, to places 365, there's a huge jump. And the trend in this domain has been that if you give a large number of data, the learning algorithms seem to be performing really well. But at the same time, we should also be looking at the aspect of how can we think about sample efficient way of learning. Probably we don't need so many samples. So there is a different set of research that is happening to think about how can we efficiently learn with a small amount of data. Or maybe the way to do it is learn from a huge available data offline, but fine tune it to your own application. So there are a bunch of ways to do that. And people have been thinking about doing it with less data. And especially in robotics, we are heavily interested in that because we don't have data like the other applications. So something to think about when you're reading the research papers, like, is it data hungry or is it like, can you do it with small number of data? Is it pre-trained or do you have to train it and all that stuff? Okay, so coming back to implementing a first classifier, let's say a nearest neighbor classifier. Like we saw earlier, there are two blocks, one that takes in images and labels and kind of memorizes what's happening in the data. and it spits out a model. And the prediction is going to use that model with a test set and predicts the labels for these test images. And when you're looking at nearest neighbor, what you're talking about is you memorize the training set, and when a new image is given as a test case, you're kind of looking up and seeing, does it match with any other images that I've already seen? If so, you just spit out that particular label. When I say that when it matches, you're talking about similarity between your test image and the existing training images. And one way to do that is using a distance metric. And here is L1 distance. Basically, what you're doing is you're subtracting test image with the training image, the absolute difference, and summing up that into one single value. This is a very simple distance function to find similarity between two matrices. And in this case, images are matrices, so we are doing it. Now, this is the code for nearest neighbor classifier, right? So if you look at it, the training is basically, you're trying to point to the data. That's it. You're kind of like saying, okay, I don't know, if people are familiar with Python, all you're trying to say is the pointer is here for the data. That's it. So it's basically memorizing the training data. And in the prediction or in the testing phase, for each of the test image, like I said, you're trying to find the nearest neighbor in the training images. So here, in this particular line, you're computing the similarity, and you're tracking which is the lowest or lowest similarity or highest similarity with lowest distance, and that is your label. And you're returning that for a set of labels here. So this is a simple nearest classifier, right? Now let us think about the computational time that is being taken for training and testing. So training here is constant time because nothing is happening. You're just pointing it to the data structure. Whereas for the testing, you're taking the test image and you're comparing with all the training images that you have. Now imagine you can do this easily for MNIST, CIFAR 10, CIFAR 100. But let's say when you're moving to ImageNet, you're talking about millions of images. And then to the places 365, we're talking about trillions of images, right? So the training is going to be super fast because nothing is happening. You're just assigning a pointer. Whereas in the testing, it's going to take a long time to output the label because it's going to look through all the training images, right? This is not what we want. We want the other way. We can afford to spend time on training because we can do that offline, either using AWS or Azure. We can run that for 10 days or 15 days. But then during the test time, especially on the robot, we want it to be running like instantly and fast, right? Because there's a good question like, what if you want to like track when the robot is moving, it should be looking at a particular object. We want to do that like, let's say 15 frames per second. So we need that to be instantly happening. So that's the problem with the nearest neighbors in general, because the training time is faster, but the testing time is too slow. But having said that, there are many methods that have come after the basic nearest neighbors. If you are interested, there is a pointer on the slide that talks about using fast and approximate methods of using nearest neighbors, because there are applications where nearest neighbors tend to perform much more better than the other modern classifiers. Yes.
Well, what are some of those?
I think medical imaging could be one example. I'm taking a guess here. Yeah. Okay. So let's see how does it look visually. For instance, let's say these are your test images, and these are all your training images. What we are showing is for every test image, we are showing the top 10 similar images starting from the left. So if we say, okay, so that is a label. Let's say the most similar image images label is your test image label. So this will be the output. So it performs like around 60%, right? In this particular example. And I want to pay attention to the first one. So this is actually a serial box, whereas the closest thing that it sees is a marker. So if you think closely, and remember the thing that we talked earlier, like semantic gap, right? The agent or the algorithm is only looking at the numbers, and we are kind of using all the numbers in this case and trying to find a similarity. It works here, but it doesn't work there. And I also want to point out to the other example, which is here. It's actually a sugar box, but kind of thinks that it is close to this one. Maybe there are patterns that it is seeing locally that seems to be correlating and giving this result. So it kind of works, but not all the time, right? So let us take another example. So this is from Cipher 10. And so the frog is being matched with a cat. Probably this is because the background is white. So if you look at all the images that is like seen closer are having white background. So it's not necessarily looking at the frog features per se, but it's just like having a pattern matching that thinks that, okay, this is probably the closest image. So we are not looking at features yet. We are just looking at a bunch of numbers and finding the similarity. Okay, so the other way to do this problem would be to look at, let me go back, to look at a bunch of results and say that, okay, out of this, I will give the mode of these labels as the outcome. Let's say we're only looking at 3 images. The output would be cat, because there is a cat, frog, and the cat, and we are going to decide that the label is a cat. So that is what we say k nearest neighbors, where you can decide what the k is. And in this slide, we want to talk about, I want to talk about how the decision boundaries are affected in these nearest neighbor classifiers. So what you are seeing here is each of these solid points are the training data. Each of the solid points in this space is a training data, and it's a 2D visualization. So you can imagine the image to be just 2 pixels, x1, x0, and x1, and we are plotting it. This is the training points. These solid points are training points. And any other pixel that is being colored with a solid, lighter background is something that you can think of being classified in the process as a test sample. So here, if you take a particular pixel that has that particular color, because these are the nearest neighbors for that particular pixel. And when you come to a particular decision boundary, you have multiple solutions in that location. So yeah, so the decision boundary is where you have the classification that would change from, let's say, purple to green. So every pixel here is a test data, whereas the solid color is the training data. So that's how you should visualize this. And now if you think about it, there are some rough or noisy boundaries, because for instance, it could be easily that when this one is, let's say, belongs to the blue label, you could have had a decision boundary like this. It need not have gone with that particular shape. So decision boundaries can be noisy if you're using nearest neighbors. And in order to smoothen the decision boundaries, you have to increase the k. For instance, that is k is equal to 1. What you're seeing here is k is equal to 3. You can see that there is a smooth decision boundary between k is equal to 1 and 3. Because you're looking at multiple labels to figure out what your label is. The caveat here is that you will also see that there are locations like this, which does not have a clear outcome. right? These are locations where you are like, I don't know what the class is. So you'll have to break the tie with some logic that says if you see all the three labels to be different, I want you to pick the one with some score or a distance or something. Or you want to say do k is equal to 1 in those scenarios. So we talked about a distance function early on, which is a Manhattan distance function, which is simple subtraction and summing it up. You can have different distance metric. So one other distance metric that you can use is L2 distance, or in other words, Euclidean distance. And that would result in a different characteristics for your decision boundary. For instance, what we saw earlier with the set of slides is this one. Whereas if you look at L1, your decision boundaries are basically a combination of straight lines, like vertical and horizontal lines. So you can see that it's basically a combination of vertical and horizontal, and then you have angle locations in certain scenarios. So what I'm trying to say is, depending on the distance function, you can have different characteristics to your decision boundary. So the k-nearest neighbor need not be only applied to image data. As long as you have a distance metric and you determine what is a k, you can use that for any data. Like for instance, it can be audio data. It could be just a data from, let's say, satellite readings and so forth. You can do classification not only on images, is what I'm trying to say. Any questions so far? Okay. So a shout out to Professor Justin Johnson, whose visuals we are actually using for these slides. So there is a link where you can play around with different parameters like the k, the distance metric, the number of classes, the number of data points. So you can see how the decision boundaries will change visually on this website. Okay, so I think the fundamental question here is, once you learn about k-nearest neighbors, you want to be thinking about, okay, for this particular domain or problem, what is the k? What is the best value of k and how do I find it? And what is the best distance metric? Should I go for L1, L2, or some other sophisticated version? And we call these as hyperparameters, which is kind of decided or guessed by the researcher or the engineer who is developing these algorithms. And this is not learned from the data. So this is something that you'll have to figure out while you're training for a particular classification problem. And it is very problem dependent. And the only way we can find out is by training multiple times for different hyperparameters and choosing the best one. And now that brings us to figuring out how to do that in a more systematic way. So let us start off with a very basic one. So let's say I give you a data set and ask you to develop an image classifier. One solution could be that I'm going to use all the data points in the data set and train my network. This is actually a bad idea because you're going to get perfect results if you're thinking about a nearest neighbor classifier, because it's already memorized that particular data point and you're giving the same data points like, okay, that's it, that's the label. You're going to get 100% accuracy. The good way to do about it is split your data into two sets. One is a train set and the other one is test set. Generally, the common number for train set would be like 80% or 85% of your entire data. And this is also bad because we want it to work on a new data at a later point. So let's say you are fixing the hyperparameter by just looking at the accuracy on this test data set. You do not know how it is going to perform on a new data. So the general way of doing this is to have three sets. One is your training set, validation set, and the testing set. And the way to find these hyperparameters is to train and validate and figure out what is your hyperparameter, and then test it on the test set that was completely not seen during your process. So this is how you evaluate your algorithm. And if you want to do it much more robustly, you can do cross-validation, meaning you can take your data and say, okay, I'm going to figure out an algorithm that performs best of all of these different scenarios. So you split the data into multiple folds and say one of the fold is for validation, and the rest of them is for training, and then you also have one portion for your testing. So you can do this multiple times to figure out what is the best case. And this is how it should be done. If you think about it like more, if you want to have a robust way. But unfortunately, this does not happen for small set of, so a larger set of data. You can only do this for a small set of data. So in computer vision community, mostly this is what happens. So they do this. But cross-validation is a good technique to come up with something very robust. Okay, so in this project, you will do cross-validation, and you will end up getting a plot like this for your project one. So what you are seeing here on the x-axis is K. On the y-axis is the cross-validation accuracy. And for every K, you will see there will be like 5 accuracies because you're doing 5 cross-validations. And you will choose the one that is average out of that as your solution. And for this particular data, we found that K approximately is equal to 7 works best for us. Okay, so a general statement about K-nearest neighbors, especially from a practical point of view, is that it's a universal approximator. If you think about it, if you have infinite amount of data, right, you are basically covering the entire state space, and you know everything about that state space. So your accuracy should be like perfect, right? But theoretically, that's not the scenario, right? Like, I mean, I'm glossing over some of the theory here. So if you're interested, you should definitely look into the theory behind K-nearest neighbors. But in general, from a practical standpoint, we can say that K-nearest neighbors are universal approximators. And an intuition way of looking at it is like, for instance, let's say you have one-dimensional data point, which is X, and let's say the classification is on the y-axis. Let's say the true function is in blue color, and you're sampling out of it for your training point. The more number of training points you have, it is going to approximate the true function. So yeah, roughly we are saying that K-nearest neighbor is a universal approximator if you have large amounts of data. Okay, so the other problem that we have in this domain is curse of dimensionality, because we want to think about how the data kind of covers the space. So if you look at the leftmost scenario, let's say we have 4 points, and the dimensions of these data is just 1. So this is how the density, how dense the data could be if they are covering the space. Now, for the same data or for the same set of points, if the dimensionality is increased by 1 more, let's say the dimension is 2, you need a square to represent a good dense distribution of that space. Now, the same thing happens when you grow 1 more direction, you are thinking about 4 to the power of 3 as a space that you want to cover to understand about that space. So unfortunately for nearest neighbors classifiers, you need to have such density to be able to cover the space to be able to classify your data points. I'm going to skip this slide. Okay, so here it's a very interesting example. Like I said, if you only use the pixel values, there is a huge semantic gap. So here is one example. On the left side is the original image, and these are kind of modified images, but they all have same distance to the original image. Right? Even if you lose a portion of the image, they have the same distance. And if you change the background or change the values in the 3 channels, you can still come up with the same distance to the original image. So this kind of tells you that maybe using just pixels as a direct numbers is not the way to do it. We also saw in some of the images from the data set, right? So I think people have also been exploring the way of using features that comes out of convolutional neural networks and then do nearest neighbors on top of it. And apparently that gives you like much more accurate results. For instance, if you're looking at this train, even if the train is like seen from a different angle or a different pose, you can see that all of these are similar images to this particular test image. So it performs better than just using raw pixel values. Okay. So that brings us to the end of the lecture. In summary, we talked about image classification with training set images, labels, and how it predicts on a test set. And we talked, I think, at various points, we talked about the semantic gap of using just numbers from these images, as opposed to what we see as humans, And we saw how the image classification was used as a building block for doing robot perception, meaning going from classification to detection to pose estimation. And we saw a few examples of nearest neighbor classifiers and how the decision boundaries varies. And we talked a little bit about the hyperparameters, which are the K and the distance metric for the K nearest neighbors. And yeah, how to choose these hyperparameters using cross-validation. Yeah. Okay, so next lecture, we will see linear classifiers, and we'll probably dig in more details into that. And by the end of that lecture, you should have enough information to start off on project 1. So I will be releasing project 1 on Tuesday. So project 0 is due on Tuesday, and project 1 will be released on the same day. Yeah. And that's it.